nucleophilic substitution reaction in haloalkanes and haloarenes. We call them SN reactions, nucleophilic substitution. Now, what is a nucleophilic substitution reaction? Let us take this alkyl halide. This is the alkyl group and this is the halogen. And now we have the nucleophile. A nucleophile is a nucleus-loving entity. It may have a negative charge or it may have lone pairs of electrons. Now this is coming in search of positive charge, a positive center. So this R group, as you know, is having minus I effect, that is electron pumping effect. And the halogen is electronegative and it pulls bonded pairs of electrons towards itself. So this halogen will leave. This bond will break and the halogen will leave as the halide ion. And in its place, the nucleophile will come and attach. So that is why we call it a nucleophilic substitution. The halogen is being substituted by the nucleophile. We categorize SN reactions into SN1 and SN2 reactions. Let us first see SN1 reactions. SN1 reactions occur in two steps. We saw that it is the breaking of the carbon halogen bond. That is the first step. Second one is the attack of the nucleophile. So when the carbon halogen bond is broken, you get a carbocation which is having a positive center. It is on that positive center that the nucleophile, or it is because of that positive center that the nucleophile is attacking the carbocation. Let us see. We'll take a tertiary alkyl halide like this. It is an alkyl halide. This bond has to break. That is, the carbon halogen bond has to break. You know that breaking of a bond requires energy. It is a difficult process and it is a slow step. This takes place slowly. So when the bond breaks, the halogen will leave with its bonded pair of electrons. And what you get will be a carbocation. This is an sp3 hybridized carbon. But what you are getting, the carbocation you are getting is an sp2 hybridized planar carbocation. This is the positive center. So this will be sp2 hybridized and the geometry will be planar. And the halide will be gone. So we said this is a slow step, and so this is the rate determining step. Rate determining step. Now in this step you can see that there is only alkyl halide present. Only one type of molecule is present, and that determines the rate of the reaction. So we call it unimolecular. This is a unimolecular reaction and it follows the first order kinetics. So it's a unimolecular reaction which follows first order kinetics. We call it a unimolecular reaction because in the rate determining step there is only one type of molecule, that is alkyl halide only determines the rate of the reaction. And now let us look at this is the breaking of the carbon halogen bond. Now let us look at the second step where the carbocation is attacked by the nucleophile. Because of its symmetrical shape or symmetry, the nucleophile can make its attack from either this side or from this side. So if the nucleophile is attacking from this side, the product you are getting will be like this. And if it is attacking from here, what you're getting will be so when you look at both the products, excuse me, you can see that the products differ only in the spatial arrangement of the nucleophile or the orientation of the nucleophile. Whereas the first product, you can see that it is retaining the original orientation. That is, it is retaining the orientation of the reactant, isn't it? This is from where the halogen left. There the nucleophile has come. Whereas in this product, the nucleophile is in the opposite direction than that of the halogen. So where the product is retaining its original orientation or the orientation of the reactant, we call it the retented product. That is, it has retained its orientation. And this is the inverted product. So you will be getting a mixture of the retented and inverted product. Or you can call it, because one will be dextrorotatory and the other can be levorotatory or enantiomers. So if it is in equal quantity, you will be getting a racemic mixture. So this is SN1 reaction. First step, it occurs in two steps. The first step is breaking of the carbon halogen bond and the formation of a carbocation. The second step is where the carbocation is attacked by the nucleophile and you will be getting a mixture of retented and inverted products. So this occurs according to the first order kinetics. It is unimolecular because in the rate determining step, which is the first step, you have only alkyl halide. So alkyl halide is the only reactant which determines the rate of the reaction. Now a few points about SN1 reaction is that stability of the carbocation formed will affect SN1 reactions. The speed at which the reaction proceeds will depend on the stability of the carbocation formed. The most stable one is tertiary, then secondary, and then primary. It will happen faster with a tertiary carbocation. Then a good leaving group, the halide ion which is leaving, the halogen which is leaving, the one that can readily depart. Iodine is a better leaving group than bromine, and bromine a better leaving group than chloride. Ions, of course, iodide, bromide, and iodide, and chloride, sorry. Then presence of polar or protic solvents. You know that they have a positive and negative charge, and then these can stabilize the carbocation and the leaving group through solvation.